Hello everyone, I'm Iman, and today we're gonna learn about pressure. So pressure is defined as force acting perpendicular per unit area. We already know that the SI unit for force is Newton, which is N, and the SI unit for area is meter square or m square. So the SI unit for pressure is Newton per meter square or Pascal. From this equation, we know that pressure is directly proportional to force and directly proportional to 1 over area. It means that if we keep the pressure constant and increase the area, we eventually can decrease the force needed, and vice versa. There are two factors that can affect the pressure. One is the magnitude of force, second, the area. Let's take a look at the real life situation. The bakers use the cutting edge of the knife instead of the blunt edge. Why? Because the cutting edge is relatively smaller in area, so the force applied to the bread is higher. This is Tang. Why Tang use continuous track instead of lots of tire like a lorry? It's because Tang usually use off-roads. To keep the pressure low, it needs to have a large amount of contact area to the road. So, all the examples shown is solids applying pressure to another solids. Do liquids apply pressure? Well, I'm see you guys on the next video. Bye!
Hello everyone, I hope you all are doing well. So today, I'm going to conduct e-learning on pressure in liquids. So what is meant by pressure in liquids? Pressure in liquids is owing to the weight of the liquid acting on the surface of any object in the liquid. Let's see this example. The pressure caused by the liquid on the fish is the owing of the weight of the red water acting on the surface of the fish A. So how do we find the pressure caused by the liquids? P equals to H rho G, where P is pressure in liquids, H is depth, rho is density in liquids, and G is the gravitational field strength. From this equation, we can see that the P is directly proportional to the H, rho, and G. Whichever of them increases, the P will be increased as well. So, what is the difference between pressure caused by liquids and pressure in liquids? The pressure caused by liquids is only owing of the weight of the liquid acting on the surface of any object, whereas the pressure in liquids will consider both pressure caused by liquid and the atmospheric pressure. Let us take back the previous example. The pressure in liquids acting on the fish is the summation of pressure caused by the liquid and atmospheric pressure. In this diagram, we are required to find the pressure caused by the liquid on the fish. So the H we are taking is from the surface of the lake until the surface of the fish. So the H is equal to 3 minus 1.8, which equal to 1.12 meter. So the P is equal to H rho G, 1.2 times 1000 times 9.81. So the P will be equal to 11.77 kilopascal. There are 4 characteristics of liquid pressure. The first characteristic is that the pressure in liquid increases with the increasing depth. The second characteristic is that the pressure at any point of a liquid acts equally in all directions. As we can see in this diagram, no matter how the thin rubber rotates, the pressure acting on the thin rubber will be the same as long as the thin rubber are at the same point. The third characteristic is that the pressure in liquid does not depend on the shape and size of the container, and the area of its surface. So no matter how big or how small is your container, as long as the depth of the water is the same, the pressure will be the same. The last characteristic is that the pressure in liquids depends only on its vertical distance from the surface of the liquid. So we can see on this diagram, the pressure of A will be the same as the pressure at B because the vertical depth is the same. We can see one of the application of pressure in liquids in U-tube. So what is U-tube used for? The U-tube is used to compare and measure the density of liquid. In this diagram, we are required to find the density of liquid P. The pressure at the point 1 and the pressure at the point 2 will be the same. So by equating the pressure at 1 and pressure at 2, we are able to find the density of the liquid P, which is equal to 833 kilogram per meter cube. So what are the other applications of liquid pressure? First of all, we can see the application of liquid pressure in dam. As I mentioned just now, the higher the depth, the higher the pressure. So the bottom part of the dam will withstand a higher pressure. So it must be built with the wall of the dam must be built with thicker material in order to sustain a higher pressure. Secondly, submarine. So in deep sea, the submarine will undergo a very high pressure. So it must be built with very thick materials and very strong material in order to withstand the very high pressure. That's all for me. Thank you for listening.
Assalamualaikum and good evening. I am Hairul from Group 10 Social Engagement. Today, I will be teaching gas pressure, atmospheric pressure and its application. Okay, let's start. First of all, gas molecules are everywhere. They move randomly and freely. Because of this, they will hit each other and the container. Thus, pressure is created inside a container. Higher the frequency of the collision, higher the pressure in a container. There are three factors can affect the gas pressure. First, container size. The smaller the container size, the more frequent molecules will hit the container. Thus, higher pressure created. Secondly, temperature. Energy can be supplied to the molecules by or through temperatures. The higher temperatures, the more energy molecules gain. Thus, more frequent collision molecule to container. Therefore, the higher the pressure. Thirdly, number of gas molecules. So, higher number of molecules in a container, the more likely gas molecules will hit the container. Thus, higher pressure created. Okay, next, atmospheric pressure. The atmospheric pressure is about 101 kilopascal. However, it is actually depends on latitude. The higher latitude, the less molecules available, thus less likely to collide. Therefore, lower pressure created. Lastly, the application. To measure the pressure, there are two instruments. First, Bourdon's gauge, widely used in engineering, and secondly, manometer. And lastly, how to calculate gas pressure using manometer by measuring the H value. So on the left, we can see a closed end vacuum. There is no atmospheric pressure presented. So simply calculated it by multiply these three values. H is the difference of height of liquid, rho is density of liquid, and G is gravity. So at the middle and right, you can see that atmospheric pressure is in the system. At the middle, atmospheric pressure is higher then the pressure gas. How do I know? Well, if the pressure at one side is higher, then it will push the liquid to the other end. So just use the formula depending on situation. Okay, thank you.
So now I will explain the instrument used to measure atmospheric pressure and gas pressure. There are three instruments for atmospheric pressure: simple barometer, floating barometer, and also aneroid barometer. For simple barometer, the mechanism is a glass tube which at least 1 meter long, and the glass tube is inverted in a trough of mercury. The height of the mercury in the tube is proportional to the atmospheric pressure. Two cases of simple mercury barometer. The first case, there is no air trap in the tube, so the bottom of the tube is in vacuum situation, and the pressure at point A will be equal to X. Also, the atmospheric pressure will be equal to H. However, when some air trapped in the tube, the pressure at point A will be equal to the sum of the X and pressure of gas. Also, for atmospheric pressure will be equal to sum of the H and the pressure of gas. The characteristic of simple barometer. When the glass tube is in different level or the glass tube is different diameter, the height of the mercury will remain the same. And also, when the glass tube is not in straight, the vertical height will still remain the same. This is a common question. Why we use mercury barometer but not a water barometer? This is because the atmospheric pressure is about 10 meter water. This means we need to prepare at least 10 meter long glass tube for water barometer. This is not practical because the glass tube may be broken, and this long glass tube is too difficult to keep and move. The second one, 14 barometer, this is an improved version for the simple barometer. So this barometer is easier to be carried around, and also the reading will be more accurate compared to the simple barometer. The third one, aneroid barometer. This is barometer which does not involve liquid, and also the reading will be the most accurate. This barometer can detect very small change in external air pressure, and the small changes can be amplified and displayed on the barometer. So next, I will explain the instrument for gas pressure, the Bourdon gauge, and also manometer. Bourdon gauge, when the gauge is connected to a gas supply, the gas pressure will strengthen the copper tube, and the copper tube will exert a force on the lever system and hence move the pointer. So the pointer will rotate and give a reading in unit of Pascal. Next, the manometer. Manometer is a U-shaped tube filled with some liquid, so usually is mercury. And the manometer can be used to measure the gas pressure in a container. The pressure of gas is equal to the sum of atmospheric pressure and the pressure due to the column of liquid. There's some notes when using manometer. Difference in gas pressure at different level can be ignored. The pressure on the surface of liquid is equal to the gas pressure in contact. Pressure that caused by liquid equal to H rho G. H means the height of the liquid, rho is the density of the liquid, and G stands for gravity. For a given liquid, the pressures at any points of the same level are the same. For different liquid with different density, the pressure at two different levels will be the different. So that's all for the instrument used to measure atmospheric pressure and gas pressure.
Pascal principle. Pascal principle states that the pressure applied to an enclosed liquid is transmitted equally to every part of the liquid. According to the formula, force equal to pressure times area, and we can rearrange it equal to pressure equal to force divided by area, where F is the force applied, A is the area on which the force acting on, P is the pressure produced by the force. So let's look at the diagram on the left. So according to Pascal principle, in an enclosed fluid, the pressure applied will be transmitted equally to every part of the fluid. Therefore, the pressure at the piston 1 will be equal to pressure at the piston 2, and we can define that force applied at the piston 1 is divided by the area of piston 1 is equal to force applied at the piston 2 divided by area of the piston 2. If the second piston has an area of 10 times that of the first, the force on the second piston is 10 times greater than the first piston, as the pressure will be kept constant, which we can show by the formula below. P2 equal to 10 F1 over 10 A1, which will be equal to F1 P1 also. Next, change of oil level in hydraulic system. When a piston X is pressed down, just as the diagram shown on the left, the piston Y will be pushed up. So the change in the volume of oil at both pistons will be equal, and therefore the change is the piston level of the two pistons can be obtained using the formula of H1A1 equal to H2A2. Let's look at this example. So a downward force of 100 Newton is applied to the small piston with a diameter of 50 cm in the hydraulic lift system. And A, what is the upward force exerted by the large piston with a diameter of 2 meter? B, if the input force of 100 Newton pushes the small piston down by 2 meter, how high will the large piston rise? Let us look at question A first. So, according to the Pascal principle, pressure applied will be transmitted equally to every part in an enclosed fluid, and therefore the pressure at piston 1 is equal to pressure at piston 2. The force applied at piston 1 divided by the area of piston 1 will be equal to force applied by piston 2 divided by area of piston 2. And when we rearrange the equation, the F2 will be equal to F1 over A1 times A2, where A1 is pi D1 over 2 square divided by 100 square to change it into meter, while A2 is equal to pi D over 2 square. And by substituting the value inside, we can find that F2 is equal to 1,600 Newton. For question B, since the change in the volume of liquid of both pistons is equal, H1A1 will be equal to H2A2. And when we rearrange the equation, we can obtain H2 is equal to H1 times A1 over A2, where we can further substituting the area of piston 1 and area of piston 2 into the solution, into the equation, and we can get that H2 is equal to 0.125 meter. For the application of Pascal principle, one of the application of Pascal principle is hydraulic brake. Let's look at the diagram. So when the driver's foot press the brake pedal, the piston in the master cylinder exert pressure on the brake fluid. This pressure will then be transmitted to the wheel cylinder of all wheels through the brake fluid and cause the piston to press the brake shoes against the wheels to slow down and stop the car.
Hello. Today I'm going to talk about Archimedes' principle and the calculations. So for the calculations part, I'm going to give some examples, and then before that we are going to go through what is Archimedes' principle really is. Archimedes' principle. What is Archimedes' principle? Archimedes' principle states that the pressure difference times area must equal to the weight. A buoyant force Fb, the difference in pressure times area, equals to the weight of displaced water is exerted on a submerged object. The object sinks to the level where Fb equals to W. Water weighs 10 Newton per liter, so every liter of water displaced produces a buoyant force of 10 Newton. Okay, next. The buoyant force is equal to the weight of the displaced water. Okay, so from here, you can see when the buoyant force is equal to the weight of the displaced water, this object will float inside the water. So that means the Fb equals to the W. So for another examples, there are three different scenarios here. So for the next part, it will happen when the buoyant force has a greater value than the weight of the displaced water. So when that happens, the object will float on top of the water. And the third scenario is when the weight of the displaced water is greater than the buoyant force. So the object will sink at the bottom of the container inside the water. The formula: buoyant force equal to weight of the fluid displaced, because there's W. So after derived, we can get the final formula of rho AHG. AH we can transform it into V, that is equal to volume of fluid displaced, times by rho, density of the water, and the G, the gravitational acceleration. A stands for area of the base of the object, and H equals to H is height of the object that is submerged in fluid. Next, this is just another example. This is just another description of the formula. Next, we are going to look at the calculation examples. So question number 1. Calculate the resulting force if a steel ball of radius 6 cm is immersed in water. Assume the density of lead is 7,900 kg per meter cube. Given radius of steel ball is 6 cm. So convert it to meter, we get 0.06 meter. So volume of steel ball, using the volume of sphere formula, 4/3 times pi r cube, we get the volume of steel balls equals to 9.05 times by 10 to the power of -4 meter cube. Density of water, rho, equals to 1000 kilogram per meter cube. Acceleration due to gravity, G, equals to 9.8 meter per second square. So based on the Archimedes principal formula that we discussed earlier, buoyant force equal to rho Vg, 1000 times by 9.8 times by 9.05 times by 10 to the power of -4, we get buoyant force equals to 8.87 Newton. Next example, calculate the buoyant force if a floating body is 95% submerged in water and the density of water is 1000 kg per meter cube. Given density of water P equals to 1000 kg per meter cube, from achieving this principal formula, buoyant force equal to rho GV. So, or we can derive it into two parts. VB times rho B times G equals to rho GV. Rho GV are the density, acceleration due to gravity, and volume of the water respectively. VB, rho B, and G are the volume, density, and acceleration due to gravity of the body immersed. Rearranging the equation, we get rho B equals to V rho over VB. So since 95% of the body is immersed, 0.95 times VB equals to V, so rho B equals to 950 kg per meter cube. So for the last question, calculate the buoyant force acting on it if a stone of mass 250 grams is thrown in water. Known the mass of stone is equal to 0.25 kilogram or 250 gram. So the buoyant force is given by F times mg, 0.25 times the gravitational 2 times by g, 2.45 Newton. Thus, 2.5 Newton of upward force is being applied to the stone. The end. So that's some simple examples and definitions of the Archimedes principle. And for that, I end this short lecture. Thank you.
Hi, I will be explaining about the application of Archimedes principle. So there are many types of applications of Archimedes principle in this chapter. So one of the application of Archimedes principle is shapes. The reason is a ship can stay afloat because the average density of the ship is less than the density of water. However, it will sink to a certain level until the weight of the water displaced is equal to its own weight. And also, ships are marked with the plimsoll line for safety purposes. The plimsoll line on the side of the ship shows the level which it can be legally be loaded under different conditions. So here is the plimsoll line. The F stands for tropical fresh, F stands for fresh, T stands for tropical, S stands for summer, and for W stands for the winter. So the plimsoll line will determine the ship which is which is suitable load, depends on the different conditions. So the second one is submarines. Submarines have special tanks called ballast tanks to contain water. When submarine is afloat, the ballast tanks are empty. In order to get submarines to be submerged in the water is pumped into the ballast tanks to increase its weight. Thus, it will submerge into the water. In order to get the submarine back to the surface of the water, compressed air is used to dry the water out of the ballast tank to reduce its weight. Thirdly is hot air balloons. A buoyant force is exerted on all objects by surrounding air. When a balloon is filled with hot air, its overall weight becomes lighter than that of the surrounding air. Subsequently, it causes the buoyancy force that acts on the balloon to be greater than its weight, thus causing it to accelerate upwards. Since the density of air decreases with height, the buoyant force on the balloon will be equal to its weight at a certain height. To descend, the hot air is released so that the average density of the balloon can be greater than the density of the surrounding air. And lastly, the hydrometer. Hydrometer is an instrument for measuring the density of liquids. The lower end of the hydrometer is filled with lead shots to keep it floating vertically. The higher the density of the liquid, the bigger the upthrust will be. Thus, the scale of the hydrometer increases in a downward direction. Big bulb enables hydrometer to float. Small bulb filled with lead enables the hydrometer to float vertically. And lastly, thin stem of hydrometer increases the sensitivity of the hydrometer. So that's all for the application of Archimedes principle.
The last subtopic of this chapter is Bernoulli's principle. For a fluid at rest, the pressure is the same at all points on the same level. However, this is not true when the fluid is moving. The pressure in a moving fluid depends on its flow velocity. Bernoulli's principle states that in the steady flow of a fluid, the pressure of the fluid decreases when the velocity of a fluid increases and vice versa. There are a few observations of Bernoulli's principle. The first one is a thin sheet of paper is held in a horizontal plane in front of the lips. Air is blown across the top of the paper. The free end of the paper will rise. The flow of air at high speed creates a region of low pressure across the top of the paper. The still air beneath the paper is at a higher pressure and a net upward force lifts the paper. Next, a filter funnel is inverted and a ping pong ball is held under it. When air is blown through the funnel, the ping pong ball does not drop when released, but is held up beneath the funnel. The air flows around the ping pong ball at high speed and creates a region of low pressure. The air beneath the ball is at atmospheric pressure and a net upward force holds up the ping pong ball. The last observation is air is blown vigorously between two sheets of paper held vertically. The two sheets of paper will be pressed together by the outside air. The air blown at high speed creates a region of low pressure in the space between the two sheets of paper. The outside air, which is at a higher pressure, presses the two sheets together. Bernoulli's principle applied to fluid flow in tube. The figure shows water flowing in a tube from A to C. The water level is highest at A with decreasing heights at B and C. This is because water flows from a region of high pressure to a region of low pressure. When a fluid passes through a tube which narrows or widens along its length, the velocity of the fluid varies. As the tube narrows, the fluid flows faster and correspondingly, pressure in the narrow section decreases. When air is blown through a tube in the figure, the region in the narrow section has a lower pressure. The external atmospheric pressure pushes the water to its highest level in this section. The water level in tube C is higher than the level in tube A because the gas is flowing from a high pressure region to a low pressure region. The last part of this subtopic is application of Bernoulli's principle. The first one is Bunsen burner. When the burner is connected to a gas supply, the gas flows at high velocity through a narrow passage in the burner, creating a region of low pressure. The outside air, which is at atmospheric pressure, is drawn in and mixes with the gas. The mixture of gas and air enables the gas to burn completely to produce a clean, hot, and smokeless flame. Next, aerofoil. The flight of an airplane is based on the principle regarding the effect of the flow of air around its wings, which are in the form of aerofoil. When the wing in the form of an aerofoil moves through air, the flow of air over the top has to travel faster to cover a longer distance and creates a region of low pressure. The flow of air below the wing is lower, resulting a region of higher pressure. The difference between the pressure at the top and underside of the wing causes a net upward force, which helps the plane to take off. Next application is insecticide sprayer. When the plunger is pushed in, the air flows at a high velocity through the nozzle. The flow of air is high velocity creates a region of low pressure just above the metal tube. The higher atmospheric pressure acts on the surface of the liquid insecticide, causing it to rise up the metal tube. The insecticide leaves the top of the metal tube through the nozzle as a fine spray. Thank you.